Hello friends, welcome back to our channel Physics and Animation. Here in this video we are going to talk about the basic principle and construction of an electrical transformer. What is an electrical transformer? Sometimes it becomes necessary to convert high alternating voltage to low alternating voltage or low alternating voltage to high alternating voltage. This is done with a device called transformer, which works on the principle of mutual induction. But why do we need transformers? The large-scale transmission and distribution of electrical energy over long distances is done with the use of transformers. Here we have two very basic equations of power and heat loss. In the equation of power, it is evident that if voltage increases, then current will decrease. And if the current decreases, heat loss will also decrease. If we want to transmit power P to a long range through a wire of some resistance R, in this case, it becomes necessary to transmit power at high voltage so that the current is lower. Lower the current, lower will be the heat loss and efficient will be the power transmission. That's why we need a device called transformer, which can increase or decrease the voltage according to our need. Basic construction of an electrical transformer. A transformer consists of two sets of insulated coils. One of the coils, called the primary coil, has Np turns. The other coil is called the secondary coil. It has Ns turns. Often the primary coil is the input coil and the secondary coil is the output coil of the transformer. Principle of working of transformer. Electrical transformer works on the principle of mutual induction. When an alternating voltage is applied to the primary coil, the resulting current produces an alternating magnetic flux, which links to the secondary coil and induces an EMF in it, which actually forces the free electrons of the secondary coil and therefore produces alternating current in the secondary coil. This phenomena is called electromagnetic induction and particularly known as mutual induction. As we can see in this animation, that the magnetic field lines of primary coil is not linking perfectly with the secondary coil. Therefore, our energy of magnetic flux is getting wasted. That's why, for holding all the magnetic field lines produced by the primary coil and link it to the secondary coil, we use soft iron core. Transformer cores are usually made up of thin metal sheets stacked in layers. The layers are laminated with varnish or other insulating material. But why the layers are laminated? Because of the changing magnetic field, eddy currents are induced in the conductive metal of a transformer core. The layers of insulation serve as a barrier to eddy currents, so eddy currents can only flow in narrow loops within the thickness of each single lamination. Let's visualize this by first considering solid iron core instead of thin insulated metal sheets layers. Let's try to understand the eddy current formation in the cross section of the solid iron core. Since the current in an eddy current loop is proportional to the area of the loop, therefore, in case of a single solid iron core, the eddy current formation will be very high, and thus there is a higher power loss in the form of a heat loss. On the other hand, if we use thin insulated metal sheets stacked in layers, the layers of insulation serve as a barrier to eddy currents. So eddy currents can only flow in narrow loops within the thickness of each single lamination. Since the current in an eddy current loop is proportional to the area of the loop, this prevents most of the current from flowing. and reducing eddy currents to very small level. Thus there is a lesser power loss in the form of a heat loss. Because transformers can up the voltage or down the voltage, they are classified as step up and step down transformers. If the EMF induced in the secondary output coil is higher than the EMF induced in the primary coil at input, then this type of transformer is called the step up transformers. And if the EMF induced in the secondary output coil is lesser than the EMF induced in the primary coil at input, then this type of transformers is called step down transformers. And this higher or lower value of EMF induced depends on the number of turns. Higher will be the number of turns, higher will be the EMF induced in the coil. So by just changing the number of turns in the primary or secondary coil, we can convert step up transformer to step down transformer or vice versa. Now let's derive the equation for EMF induced in the primary and the secondary coil for step up and step down transformer. As we know from the self-induction, total EMF induced in a primary coil EP is equal to the EMF induced in a single turn of a primary coil because of rate of change of magnetic flux d phi by dt multiplied by total number of turns in the primary coil NP, where negative sign indicates EMF induced in opposite direction of the applied alternating EMF on the primary coil at input. And now for the secondary coil. Because of mutual induction, total EMF induced in a secondary coil ES equal to EMF induced in a single turn of a secondary coil because of rate of change of magnetic flux d phi by dt multiplied by the total number of turns in the secondary coil Ns. Now by dividing EMF induced in secondary coil by EMF induced in primary coil, we get ES over EP equal to NS over NP, where NS over NP is called transformation ratio. This equation proves that if NS is greater than NP, then also ES will be greater than EP, and the transformer will be step up transformer. Similarly, if NS is less than NP, then also ES will be lesser than EP, and the transformer will be step down transformer.
Thanks for watching, friends. If this video really helps you, please don't forget to like our video and subscribe to our channel. And also press the bell icon so that you will be notified whenever we upload a new video.